Hello, everybody. Welcome to session number 28. This is Antonello Uva from Polytechnic Institute of Bari in Italy. And in this session, we'll see several applications ranging in several domains: safety, education, architecture, traffic control. So I think we can start with the first contribution, which is exploring eye gaze visualization techniques for identifying distracted students in educational VR. This work will be presented by Hitoshi Rahman, a PhD student at the University of Louisiana at Lafayette, working in the HCI lab. Please.
Hello everyone, I am Hitoshi Rahman and today I will be presenting our paper titled Exploring Eye Gaze Visualization Techniques for Identifying Distracted Students in Educational VR on behalf of my colleagues from UL Lafayette. As we all know, VR devices are now being used for educational applications like virtual lab or virtual field trips. With situations like current times, VR can be very helpful. VR devices now have embedded eye trackers where eye tracking can help students stay focused on educational content in VR applications. The main focus of our work is to help teachers visualize gaze data to help them understand where the students are looking and guide them back to focus on important objects. The main motivation behind our work is to enrich educational VR via eye tracking. We created gaze data visualization techniques in VR, which allows the teachers to detect distracted students and redirect their focus. Also, we wanted to identify the most effective techniques by doing a user study to measure and compare qualitative and quantitative performance for finding distracted students. Previous researchers have used line charts, bar charts, coordinate plots, and scatter plots to visualize fixation data. Thaniadit and co-authors in their 2019 work used an AR device to visualize students' position and gaze direction in a VR environment. Borgo surveyed guidelines and implementations techniques of glyphs, a small independent visual object that depicts attributes of a data record. Kurzal collected data from multiple users to generate a heat map-like visualizations. Most prior eye tracking data visualization techniques were developed for desktop or mobile views. We adapted prior techniques to now visualize eye gaze directly in VR. We did a comparison study between the techniques to evaluate their effectiveness for detecting distracted students. Our next section is about gaze visualization technique. All techniques work for both single and multiple student cases. Each student's gaze were represented with a unique and different color. The techniques can be grouped into two categories, where one only used the current gaze point and the other used both current point and gaze history. The first technique is called the gaze ring. This technique was inspired by the idea that many people draw circles around objects they want to draw attention to. In this technique, colored rings appear at the gaze location. The good thing about this technique is that they don't obstruct the view or the scene. In these videos, you can see both for single students and multiple student cases. The second technique, gaze disc, is similar to gaze ring. The hollow ring is now opaque in this technique. The size of the disc is reduced to minimize scene obstruction. Next technique is the gaze arrow technique. Arrows are commonly used to indicate location of objects of interest. In this technique, 3D arrows indicate the gaze with arrow tips at the current gaze point. Our next technique, gaze trail, is the first one that represents a gaze history. We implemented the trail with a particle system. It represents a 3-second gaze trail. New particles look brighter than the older particles. Gaze trail with arrows. These techniques appear somewhat similar to gaze trail, which this one uses a non-fading history. Here arrows appear along the trail indicating the gaze movement direction, as you can see in the video. A small sphere is added at the front of the trail to emphasize the current gaze point. Our last technique is the gaze heat map. Students' gaze location is rendered directly on top of the objects using a custom shader. Colors from different students combine additively when they overlap. The heat map goes quickly to emphasize recent disattention. Now we move on to the user study, which compares live gaze visualization techniques that help teachers monitor students. In the user study, our independent variables were technique types, which are the 6 different visualization techniques, and student mode, where there were either single student or 5 students gaze data. For each condition, there were multiple distraction events, and the system recorded the response time and accuracy associated with it. By mean response time, we mean time when a student becomes distracted to when the participant pressed the trigger button. The accuracy was defined as the percentage of times the participant was correct about the distraction, which means when there was a distraction and they detected it. False positives and false negatives both were counted as errors. Participants gave rating on a 7-point Likert item for 3 criteria, which will be discussed later. We also asked the participants to rank the techniques based on their performance for both single and multiple student cases. At the start of the study, we gathered the demographic data and asked the subjects to fill up an immersive tendency questionnaire. Our study was a within-subject study with 18 males and 8 females in the age group of 18 to 57 with a mean of 25 years. In the study, the subjects ran through a training scene where they practiced what they do in the trial. They were told to hold the trigger until distraction ends. And then the actual study was started, where pre-recorded single student gaze data was visualized using 6 different techniques. After each technique, questions were shown in VR and the investigator recorded their responses. Then they ranked the techniques by placing physical flashcards in order. Each flashcard had an image and name of a technique. These are our technique questions. What was the overall distraction level of the students? How well did the cue help them understand where the students were looking? How easy was it to detect the distracted students with this visual cue? And last one was, what is good or bad about this technique? This question was an open-ended question. Next is a video with the study environment. First, we'll see the training scene. Here, participants were introduced to key info via voiceovers, which emphasize verbal instructions given before or during training scene. When a button is pressed, a pressure gauge appeared above the select object, which gave a user a visual representation of how much force they are putting on trigger. The actual study environment is based on a real solar farm. When objects are selected, a voiceover gave a short educational lesson related to the object. Here we can see a participant trying the ring technique for single student cases. After the techniques for the single student case is completed, participants rank the techniques on flashcards and begin the multiple student cases. This one is the ring technique for multiple students. After completion of each technique, the participants answered these 4 survey questions. They stated their answers aloud, and the investigator stored the answers on Google Forms. Result and analysis. Performance data analysis was done with repeated measures 2-factor ANOVA, part-dependent variable, and post-hoc analysis with pairwise sample t-test. As you can see on the image here, there wasn't any significant difference in response time for either technique type or student mode. However, accuracy for all techniques was significantly higher for multiple students versus single students. Friesman's test indicated a significant difference between ranks of different techniques for both single student and multiple student cases. This plot shows the number of people who picked each technique as their most favorite technique. Gaze trail was ranked the best, followed by gaze ring and gaze disc. Gaze arrow and gaze heat map showed the weakest performance. If we look at the rank distributions, gaze arrow and gaze heat map received a substantial number of lowest rank scores. Gaze ring and gaze disc are mostly ranked above the median, but with fewer rank 1 scores than gaze trail. Post-questionnaire results. All our questionnaire items were Likert-like items, and we used Friedman's test with post-hoc analysis using Wilcoxon sign rank test. To determine significance, we used alpha value of 0.05. Gaze heat map was significantly more difficult to find a distracted student. For single student cases, gaze arrows were more difficult compared to gaze trail and gaze trail with arrows to detect gaze direction and or distraction. Also, compared to gaze ring, gaze arrow was more difficult to detect distraction. Discussions. So we can say response time was roughly similar for all the techniques. We believe by spending more time with these techniques, the variability in trial mean response time possibly can reduce. Also, we noticed that accuracy was significantly higher for the multiple student cases. One possible reason is that they tried the single student cases before the multiple student cases. Thus, they could have learned to use these techniques better for multiple student cases, even though there was a training phase. Another possibility is that in the case of multiple students, there were more gaze representations to be tracked. So if they were accurate in detecting any one of the student distractions, the system marked that as accurate. Gaze trail was most often given the top rank, followed by gaze ring and gaze disc. Showing a history might have contributed to the success of gaze trail, but we think history is not enough, as history-based technique gaze trail with arrows and gaze heat maps were not preferred as much. Follow-up work could tune the amount of history shown to discover its effects. From our results, heat map-based visualization on 3D objects are not suitable for live visualization of short-term gaze information. The heat map cannot be rendered in mid-air, and there are visual gaps in updating points when gaze moves away from an object to another object during distraction. More difficult to follow than other techniques like gaze trail, which draws a continuous path across gaps, possibly using a low-pass filter, could make the heat maps a little bit easier. And it would also avoid sudden jumps in the gaze location, leading to fewer jumps in depth. The limitations of our study is that the participants for this study were mostly undergrad students. This result could differ from experienced teacher, limiting immediate applicability to real VR classrooms. Different pupils judge distraction differently, and that can affect our results. Also, there are many other factors involved, like physical and mental well-being for attention measurement. All our subjects tried the single student cases before trying the multiple student cases, which we believe might have contributed to the better accuracy in multiple student cases. Even with the limitations, our results provide a basic step towards understanding user experiences when monitoring eye gaze directly in VR. Knowing how clear and appealing our visual cues are should benefit other applications. For future work, we would like to include more sensing data such as heart rate, skin distraction, EEG, etc. as part of our student distraction detection system. We would also like to explore how these techniques behave as the number of students increases. We used recorded gaze data of students for this experiment. In the future, we believe it would also be interesting to see the performance of these techniques with live data in a network VR application. That concludes my presentation. I'll be open for questions. Thank you.
Okay. Thank you, Hitachi, for your presentation. And let's see if we have some questions. Yeah. Okay. So there's one question. I'm not sure whether you mentioned about what was the information you gave to the students prior to the experiment. Were they informed about the gaze being monitored? Did they know the goal of the study?
Yes, thank you for the question. So what we did is we used pre-recorded student data during the study. So while we recorded the student data to check their gaze representation, we inform them about it, that their gaze were recorded for a study. And before each study started, we let the participants know why we were doing the study and what were our goals. And they also signed like pre-questionnaire, and they were given a consent form where everything was written for them to go through. Thank you.
Okay, and we have another question. What effect did the different color for each subject have, considering that the red or yellow will be more visible than the blue, for example?
So for multiple students, we use different colors. So it was they would range between red, yellow, blue, and other colors. And we do feel after the study that depending on the environment, different colors could come in more handy based on which color was more dominant in the environment scene. But yes, I do realize that like red was more visible in the scene, but for a different environment, maybe blue was more visible.
Okay, I think we have just a last question, which actually is in line with some of my concern. Do you think it's ethical to use gaze to detect distracted students, knowing that gaze can indicate disorders such as ADHD, for example? Also, it can be also related to some privacy concern in the study.
Yeah, so we did think about the privacy issues of it. So our ultimate goal is to use this in real life educational environments, and we do want to take information like we should get the consent from the students, or in case of minors from the for their guardians information, or like their consent before using their gaze data. And the way we used our study, all their gaze data were totally anonymous, so there wasn't any way to go back to like whose data was which one. So that we feel for our study the privacy was not that big an issue, but when we are doing it with an actual students in a real life educational environment, we feel that we need to talk to them about the privacy issues. Like we need to make sure that they know we are getting their eye gaze data, and only if they're allowing it to for us to use it, we'll use the data.
Okay, so if you have any other question, just please feel free to join the presenters in a room after the session. So this will be indication for all the presentation. So thank you, Hitoshi, again. And okay, so we can go. We'll be right back for the next presentation. Okay, here we are. So next presentation is presence, mixed reality, and risk-taking behavior, a study in safety intervention. And this work will be presented as a pre-recorded video by Sergand Asenfode. Sergand is with the Civil Engineering Department at Virginia Tech. Please.
Everyone, welcome to this presentation. My name is Sogan and I'm going to present our paper related to presence, mixed reality, and the risk-taking behavior, a study in safety interventions. The construction industry is one of the most hazardous industries worldwide. And despite all safety efforts, safety incidents still occur when the unsafe behavior of workers coincide with the unsafe site conditions. So human error remains the main cause for up to 80% of the incidents in the construction industry. The state of practice suggests that the most effective strategy for reducing human error is to increase the level of protection safeguarding workers by developing legislations, providing safety trainings, implementing safety standards, and compelling use of the PPE. Known as safety intervention, each of these interventions is expected to keep the hazard under control to some degree. But incident reduction from increased protection were lower than expected, which led to the question why the construction industry not experience safety returns. One hypothesis for lower than expected safety benefit of the safety interventions is known as risk compensation. Risk compensation is analogous to the thermostat of at-risk behavior, similar to the thermostat which has the set temperature and activates when the temperature deviates. Individuals adjust their risk-taking behavior based on their perceived risk and benefit associated with the situation. Also, immersive environments have been used broadly for safety training, for simulating the hazardous situation in a risk-free setting, or for phobia treatment, or even emergency evacuation training, or even intensive training in hazardous military mission. Few studies use this system to examine the risk-taking behavior of workers. So such systems are ripe for explorations of the risk compensation theory that I explained. In this presentation, we evaluate whether the mixed reality is a suitable platform for assessing the risk perception and the risk-taking behavior of construction workers. Among all trades, residential roofers are disproportionately exposed to fall hazard when installing shingles, although they were provided with the required fall protection system. So we know that we want to focus on the residential roofers and want to ask them to install shingles. But to objectively monitor the risk compensatory behavior of workers when they are on a roof and they are installing shingles, we should, the first option is to do it in a real world. But if I ask you to come with me on a roof of the two-story building and I say that I'm not going to give you any protection, you are not going to participate and I'm not allowed to run this study based on IRB. So that's why that we establish a mixed reality environment to simulate the roofing task and monitor the risk-taking behavior of workers and examine whether a risk compensation exists in the construction industry. In our mixed reality environment, virtual and the physical object coexist and interact in real time. So our virtual model depicts a suburban area in the United States consisting 1 to 2-story residential buildings. We built the model in Maya and export it to the X3D. But we render it to the first person user's position and orientation because we want to give them the feeling that they are on a roof and they are installing shingles. But we also add some like visual cues such as traffic signs or naturalistic lighting to make sure that it's visually realistic and convincing. But in order to give them that they are on a roof, we really built a physical element, the real prop, the passive haptic, which is the physical section of the roof, which is 2.4 meter by 1.8 meter with 27-degree slope, to reproduce the real environment's physical characteristic and also to simulate the touch and force channels. So the participant will go on top of this roof, but also the roof, the physical section of the roof, the passive haptic, was located on a floor, but what the participants see that they are 2-story high. Two tracking targets, the head tracking, which is mounted on the shutter glasses, and also the wrist target, which was fixed on the ankle of the participant, were used to collect the location data for each individual and to trigger the VR behaviors. So for example, if they go close to the edge and lean over, we made them fall. We didn't physically hurt anyone, but we did it emotionally because we had the gravity to our virtual environment, and we initiate the virtual fall animation if they go close to the edge and if they fall, if they lean over the edge. But we also add the wind effect using two fans, that the wind that they will experience when they are on the roof of the 2-story building. And at the same time, we also add the sound effect played like common suburban noises at 9 in the morning. For example, the birds are singing over there, the car is passing, the children are playing, all the distraction and all the environmental noises that they may hear when they are on a roof of the 2-story building. So, as you will see in the next slide, we use the mixed reality to enable workers to maintain a sense of the spatial orientation and experience a virtual fall when they get too close to the edge. In order to ensure that the participants know how to install shingles, training was provided for them before the experiment, and then they were asked to finish the task, which is installing 27 shingles under 3 experimental conditions. No safety intervention, just having the protective equipment, and then level 1 fall protection, fall arrest system, that known as the injury reducing intervention, and the third one is injury preventing safety intervention, which is having the fall arrest system and the guardrail in place. In order to remove the odor effect, the experimental conditions were counterbalanced in order to make sure that we are studying the impact of the experimental conditions. So there were three orders, which is ABC, EAC, and the CBA, and each of the participants assigned to one of these orders. The participant provided with break between each experimental condition to ensure their heart rate come back to the normal. After we are done with the experiment, we conducted a semi-structured interview, and then they received their compensation and they left. Qualitative and quantitative measures were used to track workers' motions, localize their position, monitor their physiological responses, and obtain real-time musculoskeletal data. As you can see, the Kinect motion sensors, the video recording, head tracking, ankle tracking, the activity tracker, and also some questionnaire were used to obtain information about individual characteristics and track their productivity and the likelihood of injury occurrences in terms of their perceived level of risk, their risk-taking behavior, and their safety performance. Subjective and objective measures were used to assess the sense of presence of the participants. In terms of the subjective measures, the question inspired by the study conducted by Bouchard and his colleagues in 2004. And the question that we use is that, to which extent from 0 to 5 do you feel present in the virtual environment as if you were really there? Explain. And then we continue the discussion with how did the risk perception change in each of these experimental conditions, in which condition they felt greater level of risk, and in which condition they felt more protected. We content analyze the responses to examine whether the participant changes in sense of presence relate to their behaviors, and then we double check the subjective measure with the objective measure that we collected from the sensors that I will discuss in the next slides. 30 centimeters to the edge was identified as the risky zone, and all the objective measures were collected when the participant stepped into the risky zone. The results from the self-report presence question showed that the 88% of the participants believed that the mixed reality simulation was realistic enough to simulate the height of the two-story residential building. And as you can see on the graph on the right-hand side, the vertical axis on the left shows the presence score. And as you can see, the self-report presence score were pretty high for all the participants. And the participants believed that the sound and wind effect and the realistic projection of the suburban area, the slope itself, provide them with a sense of being on a roof of the two-story building and install shingles, which are the signs of the place illusion and plausibility illusion. Also, the changes in their heart rate variability showed that, for example, under condition that they had no protection, they experienced higher level of stress, which is the lower level of heart rate variability. I should say that the heart rate variability is different than the heart rate. So higher heart rate variability is the sign of the lower level of stress, and lower heart rate variability is the sign of the higher level of stress. We will talk more about it. One of the objective measures that we used for assessing the sense of presence of the participant is their heart rate variability or their heart rate. So the results show that subjects mostly experience higher level of stress or arousal when provided with no protection. But on average, the participant experienced lower level of stress when provided with the false safety interventions, which shows that we were able to use the mixed reality with the passive haptics and the manipulation to capture naturalistic behavior of individuals. So when there is no protection, when they go close to the edge, they just feel that, okay, I'm stressed because they think that they are going to fall because they are what they see that they are 2 story high. Another objective measure is related to the proximity to the edge. Our result shows that the participant increased their risk-taking behavior by 55% by stepping closer to the edge when they were provided with safety interventions, condition B and C. Under condition C, which is guardrail in place, we were able to reduce the risk-taking behavior in terms of leaning over the edge because of the direction of the guardrail, which is towards the roof. But they introduced new risk because they over-relied on the safety intervention, which is guardrail, and lean on the guardrail toe board. The guardrail was not designed to tolerate that one, and we had some cases that the guardrail failed because of the over-reliance on this safety intervention. The heat map here also showed that the participant step into the risky areas more frequently when they had fall safety intervention in place, condition B and C, compared to when they had no safety intervention in place, which is condition A. The results of a study also showed that the choices of the participant in terms of their postural stability changed significantly under different experimental conditions. For example, under condition A, that they had no safety intervention in place, they prefer to just face sideways because they want to see the edge, they want to know that how close they are to the edge, and they prefer to sit on a roof and install shingles. But as we put the guardrail in place, because they think that they are more protected and they are not going to fall from the roof of the two-story building, they think that they can rely on the guardrail or lean on the guardrail toe boards and then face uphill, or stand or bend when they want to install shingles. They don't need to sit because their perceived level of risk about the situation decreased significantly because we already have the guardrail which protected the edge. Previous literature showed that there is a significant difference between people with a different personality characteristic and how they perceive and interact and communicate with the immersive environments. Our result shows that those that they are extrovert and openness, they also reported higher level of engagement in the mixed reality environment, and they also reported higher level of presence. And also there is a positive correlation between the extroversion and the physiological responses, so that those that they are extrovert or openness to the experience, they perceive lower level of risk when they are close to the edge. So in this study, by adopting multimodal techniques, which is synchronizing virtual environment with the passive haptics, we were able to produce a mixed reality system to capture naturalistic risk-taking behavior of workers and simulate the virtual fall hazard. So the combinations of the subjective and the objective measures help us to measure and assess the sense of presence. And it shows that the mixed reality was the optimal way to study the risk-taking behavior of workers without exposing them to the actual risk. So the mixed reality also provides a unique opportunity to raise participants' sense of presence and capture the realistic responses to safety measures, both for the research purposes and also for training purposes. Thank you for your time and attention. Feel free to contact us if you need further information about this research.
Okay. Yes. Okay, so thank you for your presentation. Let's see if we have some question. Looks like there are no question. I will do my own. First of all, very, very interesting results. I see that you claim that your mixed reality environment, which was very complete, was a suitable platform for triggering behavior changes under different conditions. It was very clear by the results. So basically, you also proved the reduced perceived level of risk in accord with the risk compensation theory. So now, did you think about using the mixed reality environment in sort of training mode to virtually raise the awareness of the risk in the workers, basically to counterbalance the negative effect of the risk compensation theory?
Can you hear me now?
Yeah.
Okay, sorry. So thank you so much for this question. I'm just telling that first we need to make first to test to see that if there is compensation exists in the construction industry, and that's why that we conducted this study. This is part of my PhD dissertation. And now the next step is to raise awareness in the construction community by providing the mixed reality training for workers to pave the negative impact of it. This is the future steps of it, of our research. Thank you for asking it, but we are looking forward to it.
Okay, so thank you again. We'll be soon back for the next presentation. Thank you again.
Thank you.
Okay, here we are back. And the next presentation will be health and safety of VR used by children in educational use case. Presenting Brandon Barca, who is a cognitive psychologist at the Phoenix User Research Center at Exponent, where he conducts applied research for a variety of industries, including usability and health and safety research. Please, thank you.
Cool, thanks. Yeah. All right. So thanks very much. I'll just jump right in. Our study aimed to assess whether VR usage by children, specifically ages 10 to 12, in an educational use case scenario results in any adverse health and safety related effects. This is of course important because these devices are already being used in the classroom, and there's some research on these topics, but not a whole lot, and in particular not a lot with current modern day VR devices. So we wanted to dig a bit deeper on these topics. A little bit of background first. So you can think of VR as potentially affecting a few different domains in terms of health and safety issues. One being the vestibular ocular domain, another being adaptation-related effects, so sensory adaptation or sensory motor adaptation, as well as potential issues related to the vergence, accommodation, conflict, which I'm sure most of you are already familiar with, so I'm not going to go into a description of that. I want to break this down a little bit further and then also show how the measures that we use in our study map onto each of these domains. So for the vestibular ocular domain, this is referring to effects that mainly arise from conflicts between the sensory streams. So if you're seeing something that doesn't agree with what your body is feeling, you can experience things like nausea or potentially disturbances in balance. And so we had a few measures that mapped onto these, including balance board measurements and a measure of the vestibular ocular reflex. And I'll talk about each of these measures in more detail on future slides. And for nausea, we used the Simulator Sickness Questionnaire, or the SSQ. For adaptation, you might expect sensory adaptation related effects for things like depth perception, visual depth perception. And for that, we had a number of measures that map onto that to assess that. And for sensory motor effects, one of those measures also assesses that. For vergence, accommodation, conflict-related issues, we use the SSQ as a subjective measure of eye strain or other types of ocular discomfort that might arise. And then as a more objective set of measures, we had a set of ophthalmological measures that measured specifically ocular and visual-related potential effects. A little bit about our methods. So we had 30 kids in the study, ages 10 to 12. There was an equal distribution of males and females. And for VR usage, they each used VR for 30 minutes per day across 5 days in a row. And this was intended to simulate a potential educational use case scenario wherein you might expect a teacher to have, say, a particular project where kids are using VR across multiple days, seeing different things. Past studies have done single-day exposures for anywhere from 20, 30 minutes up to an hour, but no studies have done multiple days of exposure, so we wanted to push the envelope there a little bit as well. There were 5 different VR devices used, including the Google Daydream, the Vive, the Rift, the PSVR, and the Gear VR. And these were evenly distributed across the participants, so 6 kids per device, just to get sort of a good sampling of the types of devices that are currently available on the market and that are being used in these kinds of scenarios. And then each device was preloaded with content that was that were selected specifically to capture certain elements of expected educational VR experiences. So that included both content that had passive viewing type elements, so like where the users are just sort of taking in information that's being presented to them, as well as content that had more interactive game-based elements, because of course, especially in the case of a VR platform, a lot of educational material is going to have more of a gamification of the learning elements. We wanted to make sure that we covered all of those bases on each of the devices. So a little bit about the measures that I mentioned. For the ophthalmological measures, we measured visual acuity, both near and far distance with a 4-opter and a digital Snellen device. For phoria, or ACA ratio, we used something known as the alternating cover test, which provides a measure of the position of the eyes when fusion is disrupted. So this is a measure of vergence, so part of that vergence accommodation conflict. So if there's one of the eyes is deviating either inward or outward, you can get a measure of that, as well as the magnitude to which that's happening. And then we had a measure of accommodative facility with the flipper test, which is a measure of the eye's ability to change their focus when switching between different viewing distances. Again, a good measure of accommodation in this case. And then also we had a measure of stereo vision, stereopsis. So this used a stereo vision test kit that had polarized glasses and 9 different levels of binocular disparities to give us a measure of stereo vision. For balance, we had a research grade balance board that provided us with 3 different metrics of balance disturbances, including a measure of the total sway area during the measurement time, a measure of the anterior-posterior variance, as well as lateral side-to-side variance. And those 3 measures were collected under 4 different conditions, including with the participants' eyes open during measurement, eyes closed, as well as with and without cushion underneath their feet. To measure sort of the link between the vestibular and the ocular system, we had a measure of the vestibular ocular reflex known as the head impulse test. This is done when you rotate the participants' heads in either direction, and they don't know when you're going to rotate. Their instruction is to keep a fixation of their eyes on the tip of your nose. And if everything is working as expected with this reflex, when you rotate their head, they should be able to maintain fixation on your nose. But if there is a disconnect between the vestibular and the visual system, then it would look more like this bottom series where they're on your nose, you rotate their head at an unexpected time, and it breaks their fixation on your nose, and you see them correct. So that would be an indication that there's an issue with this reflex. For near distance depth perception, we had something known as the skewer straw task, which is a good measure of hand-eye coordination as well as stereo vision. In this task, it's a timed task where they have to insert wooden skewers into a set of straws as quickly as they can. It's a good diagnostic test. For more far distance depth perception, we use something known as the blind walking task, where a participant starts at a starting line. They're allowed to view a target location. They are then blindfolded and they attempt to walk to that target and stop on top of it. And the experimenter then can take a measurement of the difference between where they stopped and where the target actually is. So you get that delta, and you do this multiple times across several trials, and you can do it for both a near and a far target. And then finally, as a measure of subjective comfort, we use the Simulator Sickness Questionnaire, which of course has 3 subscales that assess things like nausea, ocular motor discomfort, and disorientation. All of these measures were recorded at 3 different time points, including before any VR use. So day 1, pre-VR, to get a baseline measurement. And then after the 5 days of VR, there was a post-VR measure. And then we had the participants come back for a 6th day, so for like a 24-hour follow-up where there was no VR on that day. The only exception to this pattern of data collection was for the SSQ, which was only recorded after VR usage. So this pre-VR measure on day one was actually a post-VR. That's because past research shows that a pre-test measure of SSQ can actually artificially inflate SSQ scores due to demand characteristics, so we wanted to avoid that. All right, so the results for the ophthalmological measures, for all 4 of them, there were actually no adverse effects or anything. They all came out great, which was reassuring. For the balance measures, again, everything came out really nice. For each of these, you can compare the blue column to the others, the blue being the baseline and then the greens being the various posts. We did 2 post measurements actually on day 5 for this, separated by 20 minutes just to see if there was any change in any effects that we might have gotten after a delay. There was one significant effect for the anterior posterior sway in this condition for the first measure on day 5, but it was actually a significant improvement in balance, so no worries there. There was one significant decrease in performance for just one time point. That was day 5, the second post measurement compared to baseline, but it was a pretty small effect. And I think the overall pattern is what you really want to consider here, where everything's pretty much flat compared to baseline. And the few points where you see a spike, those are non-significant results. So no real issues with balance. For the skew wrist draw task, again, this was the hand-eye coordination task. Again, no significant adverse effects here. There's a few seconds increase after VR, but this was not statistically significant. For the blind walking study, after VR on day 5 for both the near and the far distance measurements, again, no significant difference compared to baseline. You do see an increase on day 6 on the no VR day, which is odd, but if you want to take a look at this, this is hard to explain quickly, but there's a known artifact in this task where when participants perform this task over and over across several trials, they become more and more comfortable with this task and use longer strides and walk faster and just drift outward, just with not having anything to do with whatever manipulation you're doing. It just has to do with just repeating this task. For this reason, actually, I would not recommend using this task. I would actually suggest going to a blind tossing task, which is a sort of a sister task for this, which would avoid this artifact. And then for the SSQ, if you compare the post-VR measures on day 1 and day 5, they're definitely numerically higher than, say, the non-VR day. So it does suggest that they are having some sort of simulator sickness-related effects to some degree. But if you're familiar with SSQ scores, and if you compare this across other studies, these are actually pretty low scores even after on day 1 and day 5 of VR. Usually these scores range in the 20 to 50 range for cyber sickness. So not too concerned about those scores, and they seem to be transient in any case. So some conclusions. So overall, we find that these measures indicate that when used responsibly, modern VR devices seem to be safe for kids to use in an educational use case scenario, which is great. There are, of course, limitations that should be considered. One of which is the fact that this study was designed specifically to assess short-term VR use by a specific age range and a specific use case scenario, so you wouldn't want to extrapolate outside of these study parameters. You would need to do some follow-up research for that, of course. So, for example, in particular, this study does not address longer-term VR use, which I think is still an open question and an important one, which hopefully future studies can start to address. And then the study also doesn't address whether different types of VR content could have differentiating effects on kids, which is something to consider, especially from a psychological perspective. I think that's something that future studies should take a look at. And that's all I got. I'm happy to take questions.
Okay, Brandon, thanks for your presentation. Let me have a look if we have question on Slido. Looks like there are no questions. So yes, I have a question. Okay, so you conclude that modern VR devices can be used safely by children and you test on a specific age range, which I suppose is 10, 12, I guess, if I remember correctly.
Yep.
There are, and you say that, I mean, beside this range, you cannot extrapolate results. But actually, different recent paper have reviewed the use of VR-based treatments in autism spectrum disorder in children. In your opinion, do you think that some of this study can be extended to the subject to see? I mean that kind of particular subject is very fragile, so we need to act very carefully with them.
Yeah.
So do you think there are some possibilities to extend your study, or at least the methods that you apply for them?
Certainly the methods, I think, would be applicable. I would be cautious to extend our results and to just assume that it would be okay for an autistic population. You said autism, right?
Yeah.
Yeah, just because so much of this is going to be, the concerns really are about sensory adaptations. And we know that autistic children have different sets of sensitivities to sensory inputs. And so you never know if they could it could be affected differently by VR. But certainly the measures that we use or similar ones would be a good first step to looking at that.
Okay, so thanks again, Brendan.
Okay. Thank you.
And we'll be back for the next presentation soon. Yeah. Hello, we're back for the next presentation, which is design and evaluation of a tool to support air traffic control with 2D and 3D visualization. And this work will be presented by Victor Oliveira, who is a researcher at St. Pölten University of Applied Sciences in Austria. Please.
Okay, thank you, Antonello, for the introduction. This work is also done with the support of our partners at Fraunhofer and Frequentis at Austria, which develop systems for air traffic control, and also the Aerospace Research Group from the University of Salzburg. And I think I'm going also just to jump into it. Since we are working Atlanta time, I think it's good to start with a picture of the Hartsfield-Jackson Airport in Atlanta. It has actually the highest air traffic control tower in America and is also the busiest airport in the world. It manages more than 2,000 arrivals and departures a day. This fact might not be as new or interesting for many of us, as we know that flying is a very conventional way of traveling, especially if you talk about international trips. And if we just take a look on the air traffic control worldwide, we can see that every year we have more flights in terms of millions, and flying also is getting much more safer as we have less accidents and less fatalities as well happening. What many people might not know, though, is that the responsible for handling the air traffic control is the air traffic controllers. Particularly approach and terminal controllers are the ones responsible, many other things, to ensure that the airplanes are at an appropriate altitude when they are handed off to another control responsibility. And for many decades, the main tool used for controlling air traffic is the radar, as you can see here in this picture, which is actually a 2D visualization. And then the altitude of the airplane is represented only by digits, which the ATCO has to put together with this visual information. when we go to the European context, we have the Single European Sky Air Traffic Management Research, or CSER, which in the past few years and for also the next years has the responsibility, in between other things, to make sure we can increase traffic and reduce delays and improve safety, and all of that while decreasing ecological footprint. And to reach that, they want also to introduce for the trajectories in a way that we have a more optimized air traffic management and also support more efficient flight profile. So we can go from this traditional profile to a more optimal one. To be able to get that, we have been researching and exploring different concepts for visualizing air traffic to support the controllers to do this job better. And in the context of our project, the Virtual Airspace and Tower, we have been running for 2.5 years since 2016 under the funding of the Austrian Research Promotion Agency. And during this time, we have done interviews with many stakeholders in the field, interviews with HCOs from Austria, Germany, Bulgaria, and workshops to design more than 12 different concepts for 2D and 3D visualization, which includes touch tables and tablets and headsets for augmented and virtual reality to come up with a final prototype, which was evaluated with focus groups, designed and assessed as a low fidelity prototype. And we used all of this knowledge to come up with this final version that's assessed in this publication. And all of this process is well documented also by previous publications as well. So this final high fidelity prototype then is actually a air traffic simulator, connects to a flight database in which we store real flight data, and is connected to our audio input and output module and our user interface, which has information about planes and also turbulence categories, system time, current tilt angle, compass, but most importantly, that allows the HCOs to switch between orthographic and perspective views on demand. So finally, now with this final prototype, one question that we still had was how the HCOs would perform and perceive the 3D alternative in comparison to the 2D visualization, which gets closer to the conventional tools used by them. So that's why we defined two conditions then. For our 2D condition, we fixed the interface in the orthographic view. And for the 3D condition, we fixed the interface in a perspective view. And for both of them, controls and information about airplane are kept the same in both conditions. To help us evaluate this, we counted with the participation of 17 participants from 21 to 52 years old, and we splitted them in two groups. 11 of them were our approach controllers, or HCOs, who operate in different airports in Austria and had a work experience varying from 4 to 29 years. And we also had a smaller group of 6 non-HCO participants, which we were recruited from students reporting having high experience playing 3D games, so we could have a control. So every participant in this study started with an introduction about the test for 5 minutes, and then went through a training phase for 35 minutes, in which all of them could just explore the tool in 2D and perspective views, see information about the airplanes, make questions, understand the controls. And then they had to perform the task, which was efficiently and safely land as many airplanes as possible, which they did with the 2D for 30 minutes, and then the 3D for 30 minutes. And after each task, they had to answer questions related to situational awareness and workload. And after the whole experiment, they have to answer questions about user experience and also some ad hoc questions in a semi-structured interview. The data used for this experiment was real data recorded from the Frankfurt airport from 2018. And we collect data from arrival and departures from one day. And we use different times of that same day for the training phase and for each one of the 2 tasks. Okay, so here you can see a summary of our results. When it comes to situational awareness, which we collected with the Sasha-Q questionnaire, we could observe that the 3D, during the test, the 3D condition helped the participants to yield higher scores for situational awareness. When it comes to workload, the 3D also yielded lower workload compared to the 2D. And in particularly, we could see that mental demand was lower for the 3D, while temporal demand, effort, and also frustration were higher for the 2D. The mental demand was also higher for the students in comparison to the HCOs. When it comes to performance, the number of landed flights normalized according to the data used. We could see that the HCOs landed more planes than the students, as expected, and they also deviated less from the optimal route that could be calculated from the simulator. We could not see any differences for the flight duration. Finally, for our user experience questionnaire, we could see that overall the students had a better experience with the system compared to the HCOs. And when we take a closer look in the benchmark provided by the questionnaire, in which it's compared to many other systems, we could see that the students reported a very good experience for many factors, including active-attentiveness, perspicuity, efficiency, and dependability, but not as good for novelty. While the HCOs, on the other hand, provided lower scores for the experience regarding many factors, but stimulation and novelty, in which they rated as excellent. What that means then. So if we just think about those results and we take a look in previous work in which 2D is compared to the 3D interface overall, we can see contrasting results in which, for instance, Cockburn and Mackenzie has shown that user performance decreases when moving from a 2D to a 3D interface, while Tabanti and colleagues show actually an improvement. In our experiments, we cannot really attest about performance of the user, but we could really observe that participants had higher situational awareness and lower workload when using the 3D variant only. Previous work also assessed different interfaces to support air traffic control. Many of them also included the air traffic controllers in the process, especially on requirements and final assessment. But in our case, we try to include the HCOs and the experts during the whole process. So we hoped that these multiple iterations would help further improving the validity of our prototype. And we were happy in seeing that the HCOs during our experiments could actually translate this previous experience that they had to our tool and outperform the students. So even though it was expected for them to outperform the students due to their experience, it was good that they could do with our tool as well. Finally, we can see that the generalizations overall regarding performance are not really possible to do due to lack of difference between the 2D and the 3D conditions when it comes to performance, but also in terms of assessing a specific tool and also regarding stimulus presentation order. But overall, we could also observe that user experience also counts greatly in this context, even more than performance. So performance is very important, but we could see that even though HCOs could perform well with the 3D condition, they reported lower user experience, and perhaps is due to familiarity with the technology. So we would say that for further studies on this topic, not only performance should be investigated, which is really important, but mostly solutions on how to maximize acceptance, especially for expert users, which are not 3D UI experts, but really like work expert users. So finally, in our study, we could design this tool to support air traffic control using the 2D and 3D visualizations and assess this tool with different end users, but especially with the participation of the HCOs, and argue and discuss a little bit about the acceptance of 3D representations by work domain experts. Yeah. So I thank you all, and I'll be open to questions. And just to finalize, it's not related to this study, but it's still available on Hubs. You can just visit our demo related to the 3D UI contest. Okay.
Thank you, Victor. So let me see if we have any question from the audience. Yeah. Okay. So we have a question. Can you elaborate a bit more on the task when using real flight data? How were the participants able to give the pilots any direction? What were the concrete interactions the participant had to perform?
Well, good question. So the data was simulated based on the real flight data, but we just had a virtual pilot. So through the controls, the participants could define the direction where it should go, and then see the airport and plan the route until the landing. Yeah, so basically that.
Okay, so I have another question from my side. So you basically compare like a 2D interface with a 3D interface, but both of them, they were kind of synthetic design for this test. So how far is or are those two interfaces from the real interfaces the operator are using in the daily work? So basically, do you have a baseline to test those two interfaces, or they're just comparing those two abstract interfaces?
That's a good question. So the interface was done with the collaboration of the HCOs and was done looking or in consideration to the interface they are using. But for sure, it's not similar, and we do not have fully access to the ones that they really use in terms to run the radar as a baseline with this one. So for sure, it's not shown how they outperform even the 2D, outperform the radar. But yeah, overall, it was really done with their assistance. Yeah, so we only have these as metrics, like their participation in the process of designing it.
Okay, so thanks again, Victor. And we'll be back for our last presentation soon. Thank you.
Thank you. Bye.
Yes, hello everybody. We're back for our last presentation of the session, which is Learning in the Field, Comparison Desktop, Immersive Virtual Reality, and Actual Field Trips for Place-Based STEM Education. And this work will be presented by Jia-Yan Chao, who is a fourth-year PhD student at the Department of Geography at Pennsylvania State University. So please.
A PhD student from Penn State. So today I'm here to present my work about how to use immersive virtual reality to facilitate geology learning in the context of place-based education. The title of my presentation is Learning in the Field, Comparison of Desktop, Immersive Virtual Reality, and Actual Field Trips for Place-Based STEM Education. According to many educators, field trips are a key component of learning in many STEM disciplines, such as geoscience, to develop skills, integrate knowledge, and prepare students for lifelong learning. Field trips help bridge formal and informal learning, and students have the opportunity to study in the real world and learn from interacting with raw natural materials in order to reinforce knowledge acquired in the classroom or from the textbook. However, especially for undergraduate students, learning in the field can present many challenges due to issues such as safety concerns, and the field site may not be accessible for all students. During the field trip, some students may not be able to gather around the instructor due to the broad or rugged terrain. Additionally, the instructor has no control over environmental distractions such as inclement weather, lighting, and traffic noise, which may lead to a less ideal learning experience. In light of these practical challenges, researchers and educators have made effort to deliver the digital version of field trips to students. Such virtual field trips allow students to observe and interpret geologic phenomena as well as practice fieldwork skills in the classroom or at home without the need to go outside. For example, researchers at Arizona State University designed a colorful array of web-based virtual field trips that can be experienced on desktop displays. Users can browse different multimedia resources, rotate their view in 360 degrees, and navigate to new locations using the mouse and keyboard. On the other hand, with immersive virtual reality entering the mass market, the emergence of IVR technologies leads to incomparable opportunities for researchers to advance virtual field trips to an unprecedented height. Immersive VR possesses a higher level of immersion than the standard desktop computer. First, surrounding indicates the extent to which the physical world is shut out. Thus, the head-mounted display of IVR should possess a much higher level of surrounding than a computer monitor with limited field of view, while users can still see their physical surroundings outside the edge of the desktop screen. Second, matching considers how well the technology approximates actions and movements in the virtual space. For example, IVR systems use external tracking sensors to enable real-time position and orientation tracking such that users can physically move in the virtual world. In contrast, desktop users typically use a more abstract navigation interface, such as mouse and keyboard, to look around without actually moving their body or head. As a result, IVR should be able to induce a stronger sense of being in the virtual world, that is, the sense of presence, than the desktop display. It is important to notice that, despite the highly engaging experience, learning about geology in IVR is still an understudied phenomenon, and it is not clear whether using IVR to teach about science would lead to a better learning outcome or not. By mimicking natural embodied interactions from an egocentric perspective, a highly immersive experience should lead to a positive learning effect, because it provides users with an embodied and authentic learning environment. However, some studies have shown a reversed effect of IVR on science learning. In some scenarios, the added immersion that is not directly relevant to the instructional goal might be categorized as seductive details, which may distract learners from the actual learning content. Given the mixed effect of IVR on science education, new research is needed to examine the role of immersion that comes into play when students learn about geology. First, we want to investigate whether IVR is an effective medium to generate positive learning outcomes compared to the traditional desktop computer. Second, we want to assess the effectiveness of virtual field trips by comparing the virtual with the actual field trips with respect to students' learning experience and perceived learning outcomes. The Sonola Lab is part of a geoscience introductory laboratory course in Penn State, which includes a site visit to the Sonola Formation in Pennsylvania. The actual field trip was led by teaching assistants and lasted 30 to 45 minutes. The virtual version was created with Unity 3D and closely mimicked the actual field trip experience, including the order of the site visit, delivered teaching content, and additional information that students had access to during the field trip. A total of 12 discrete locations were rendered by 360-degree images for the general site exploration. During the virtual field trip, students were able to navigate to other locations by selecting arrows on the ground, and they were also tested on their knowledge acquisition from the Sonola Formation during the virtual field trip using multiple choice questions. Students could also select information icons staged onto the 360-degree image to access supplementary information from the lab manual or higher resolution photos. The 360-degree image, along with each piece of additional information, was associated with an audio narration that was pre-recorded by the course instructor, which can either guide students to make on-site observations or explain specific features of the Sonola Formation. Leveraging cross-platform support of the Unity game engine, the Sonola Virtual Field Trip was developed both as a standard desktop and a Vive Pro version with the same content and features. Specifically, the strata measurement task was designed differently in desktop and immersive virtual field trips. During the measurement, IVR students can walk around the photorealistic outcrop model and use the virtual ruler attached on top of the Vive controller to perform the measurement, while desktop students were placed in front of the outcrop and simply used the mouse to draw nodes on the rock surface for length measurements. In total, 52 undergraduate students were recruited from an introductory geoscience laboratory course. There were 2 VFT groups, desktop virtual field trip and immersive virtual field trip. Besides, we also included a control group in which students only took part in the actual field trip. The experimental procedure was different for the VFT and AFT groups. VFT students answered both pre- and post questions, whereas AFT students only need to complete a post questionnaire. The procedure shown on this slide is for VFT students, while AFT students only answered those questions marked by yellow after their field site visits. For the comparison between desktop and IVR, we focus on the VR-specific experience, that is, simulator sickness, VR features such as the representational fidelity, system usability, presence, and in-VFT test performance. The results indicate that immersive VFT students reported higher self-location scores or presence and greater levels of simulator sickness than desktop students. Leveraging the position tracking and the larger display field of view, IVFT students had access to their surroundings by using the same embodied activities used to look around in the real world, which could result in a greater sense of presence or self-location. On the other hand, such embodied and egocentric access to an environment may be associated with simulator sickness in some cases. In contrast, position trackers were not used with the desktop display, meaning that the desktop virtual field trip could result in less sensory conflict and hence induce less simulator sickness than the immersive virtual field trip. Next, we examined the main effects of AFT, immersive VFT, and desktop VFT on perceived learning experience and learning outcomes using one-way ANOVAs. We also followed up with Bayesian ANOVAs to boost statistical power for non-significant results. As we can see, for the perceived learning effectiveness, although there is no significance, a Bayesian factor of 1.08 indicates that there is anecdotal evidence supporting the alternative hypothesis. In other words, the perceived learning effectiveness reported by different groups seems to be different with each other. Our results suggest that learning geology in immersive virtual reality was not more effective than the traditional desktop display. One possible explanation is that, given its heavy dependence on 360-degree imagery, the current form of immersive virtual field trip did not take the best advantage of IVR features. For example, walking, as an important affordance of room-scale VR applications, was not fully supported in our 360-degree based VFT experience. Second, results could also be explained by the possible different image qualities. In fact, we built both types of virtual field trips using the highest possible resolution in the Unity settings. But interestingly, participants who had experienced both virtual field trips in our pilot study indicated that 360-degree images rendered on the desktop display appeared to have higher resolution than on the Vive Pro HMD, which may potentially compromise the advantage of IVR in learning geology. Finally, if we take the desktop and HTC Vive together as a VFT group, VFT students overall reported a better learning experience as well as more positive perceived learning outcomes than students who went on the actual field trip only. So, take-home message. First, while the beauty of field trips for STEM education has been well demonstrated in literature, the reality of field trips may not be perfect for students to learn knowledge. There are still a number of practical challenges of actual field trips that may prevent students from effective learning. Alternatively, we feel that virtual field trips have the ability to overcome at least some of these challenges. Therefore, virtual field trips have the potential to support and enhance field-based learning activities in geoscience education. Last but not least, IVR that supports fully immersive and embodied experiences may play an irreplaceable role in some learning situations. But at least for the range of learning objectives and activities in the current VFT, a standard desktop display with the mouse and the keyboard seems to be enough to fulfill the needs for learning geological principles and concepts, especially given that the IVR system is more expensive, less comfortable, and more difficult to set up. Thank you for listening my presentation. I will be on the Zoom for any questions you may have. Thanks.
Yes. So thank you for your presentation. So let's see if we have question from the audience. Yes. So first question: is this software available for purchase or use for other educational institutions? And if now, do you plan on making it available? This is something which is, if I can add, very interesting in this lockdown situation. Here in Italy, we have a pretty serious lockdown, so all this field trip are basically banned for the next months. So would be very supportive as a tool.
Yeah, this is a great question. So actually, we're currently making huge effort to make everything we developed available and free to other institutes and researchers. So actually, if you're interested about this experience, just send me an email so I can send you the package of the Vive version as well as the desktop version. And the other thing is actually there's a limitation of the product, which is only available on the Windows system. So now we are in the process of developing a web version, so which can be used for both the Windows and Mac users. So anyone can use that using their laptop at home. So I think that would be very useful in the current situation.
Okay. Yes, we have 2 more questions. I think we have a few minutes more. So, so do you think that the resolution of the 360 degrees images could affect your results?
Yes, I believe that will affect my results. Actually, that is one of the limitations. So because the current format of the virtual field trip does not make the best usage of the virtual reality. So the first reason is about the 360-degree image, because it limits the walking ability of the users, so users cannot walk around. So which is a very unique feature of the IVR that can afford to the users. And the other thing is about the feature of the outcrop, so which is like a flat, like a plane in front of users. So actually, there's no need for users to physically rotate their head to look around. So they just need to look in front of them. So that's the other reason that why there's no difference between the desktop and VR users. So definitely the 360-degree image is we believe is the one reason that why there is no difference between the two conditions.
Okay, last question is, could you talk a bit more about how you design the learning experience and choose the topic of geology over other STEM topics?
So the first reason is that I'm from the Department of Geography. So actually geoscience and geography belong to the same college. So we have a good relationship about different chances to collaborate with each other. So that's the one reason we have the good resources to get in touch with the faculties from the Department of Geology and Geoscience. So that's the first reason. And the other reason is that for the geoscience, there's a huge undergraduate level introductory laboratory course. So there are more than about closely to have 200 students in the course. So that means if we want to do some study about their like user study or other experiments, it's very convenient for us to reach out a very large sample size. So that's the second reason. And the third reason, of course, geology is a representative discipline in the STEM education. So because it requires students to use their spatial thinking as well as other like mathematical or other quantitative methods to do the research as well as study this discipline. So we think this can be a good representative of the place-based education in the STEM. So
okay, so thank Jiayan. Thanks for your presentation. And I think that this session is over. I would just encourage all the participants maybe just to hang out in the virtual room number 2, which is the room of the section, just to meet and maybe ask more questions to our presenter. So thank you again, and hope to see you in the virtual room. Thank you again.